Okay, I think we need to start because otherwise we will go over time. So thank you for welcome to this PASC16 flash session for posters. The idea is that we give the opportunity to people presenting a poster to actually advertise their poster and tell us why we should go to look at that, at their posters, and why maybe we should vote for their posters. The poster session is tonight, this afternoon from 5:30 until 7:30. Please remember to vote. There will be boxes all over the garden floor. So it's really just go around and then vote so that tomorrow we can actually give out our awards. So the way we are going to proceed is the following. These are the scientific fields where the poster the poster were submitted. So we will start with climate, followed by computer science and mathematics, emerging domains, life science, posters in materials, physics, and solid earth dynamics. So once I call the climate and weather posters, I would like to have all the presenters in this scientific field to come on the stage, and then you present your poster. You present yourself and your poster mainly, and you have 30 seconds strictly. So I will cut you if you exceed your 30 seconds. I won't be nice, I will be kind of rude. So please, the climate posters, and if you remember your number, you can already order yourself by number. Oops. So we are ready. This is a microphone for you, please.
Okay. So in the physical parameterization sections of weather and climate models, when seeking aggressive GPU performance requires code transformations that sacrifice CPU performance. We are developing a tool that can perform these transformations automatically and therefore provide better performance portability. Specifically, we seek to automate this through domain-specific code abstractions that exploit the property that columns in the vertical direction are independent of one another.
And thank you.
I actually hid a treasure map in mine, so come look at it.
Please.
Hi, I'm Nicolina, and I'm a postdoc at ETH Zurich, and I'll present a poster on climate change simulations at the kilometer scale resolution. And at this resolution, we can we start to resolve deep convection, which means that we start to resolve thunderstorms and rain showers. And if you want to know how we can benefit from this resolution in a climate change projections, you should come and see my poster. Thank you.
Thank you very much. Next.
Okay, my name's Doris. I'm also working at ETH Zurich on global climate modeling, and my poster is about having a global climate model that's technically up and running and now getting it to giving us some physically sensible results, more or less. More specifically, it's about tweaking subgrid scale parameterization in a model that's kind of costly in terms of CPU and complex.
Thank you very much. Okay, this first session worked perfectly well. Thank you. So the posters in computer science and mathematics, please. Thank you. If you remember the number of your poster, order accordingly. Wow, this is a massive number of posters. You are a very prolific field. Who starts?
So I'm 10.
So go, then you can count, right? 1, 2, 3, 4, 5.
Yeah, no, so we start this direction.
Yes, the microphone is here. So the number 1. Okay, so please, number 1 is, go ahead.
So hello, my name is Juraj Kardoš, and together with my collaborators, we are using interior point method to solve the boundary control problem. It is optimization problem that has equality constraints on the state and on the bounds on the control. We also use sample average approximation to incorporate uncertainty into the model, and this results into vast linear systems, and we propose sure complement to solve this system. Thank you.
Thank you very much. So you can go maybe, and so the next person can start. Please.
Discretizing a curved geometry leads to constant, non-constant access patterns. So in a matrix-free finite element implementation, every time when a stencil is applied, it has to be reassembled first, and this is quite expensive. And here I present a novel approach that replaces this expensive stencil assembly by a cheap polynomial approximation, but maintaining the accuracy and showing excellent performance. And it works for general geometries, so it may be interesting for some of you.
Thank you. Next one is Paolo Gorlani. Please, go ahead.
Hi, I'm Paolo. I work nowhere. I've designed a code which solves an hyperbolic elliptic problem using GPUs. In particular, I implement a matrix vector product which is best suited on GPUs and use extensive nothing. Then
that's okay. Thank you very much. Next one is Sebastian Cook.
Okay, hi, I'm Sebastian. So my main research focus lies in automatic code generation for highly scalable and highly optimized geometric multigrid solvers. For that, we're developing an external DSL, a multi-layered DSL. And in our recent efforts, we've proven or shown that we can do this for real-world applications, namely the simulation of non-Newtonian fluid flows. So if that's something you're interested in, just drop by my poster and we can talk about it. Thank you.
Thank you very much. Next one is, oh my God, Perumal, please.
Thank you. Hi, I am representing Cloud Lightning, an European Union-funded research project. The aim of this project is to create a new provisioning model for cloud using the principle of self-organizing and self-management. We are using 3 use cases. You can see them. Those are HPC applications, ray tracing, genomes, processing, and oil and gases. The expected impact to the cloud service providers are increased competitiveness and easy accessibility for cloud, for HPC workloads, and energy efficiency, of course.
Okay, thank you very much. Next one, Tobias, please.
Thanks. So I have a poster on DCUDA. DCUDA is a new programming model for GPU clusters that combines CUDA with remote memory access and notifications. The main benefit of this programming model is that it provides automatic hardware-supported overlap of computation and communication. And if you're interested how this works, come by and see my poster.
Thank you very much, Tobias. Next one is Demosthenis, okay, please.
Hello everyone, I'm Demosthenis Pasadakis and I'm a student of the Institute of Computational Science at UZI. My goal, together with a senior researcher Drossos Kourounis and Professor Olaf Schenk, is to estimate the drag and lift coefficients for an incompressible steady-state flow of a Newtonian fluid over domains with periodic roughness. In order to do so, we use Phoenix as a software, employ adaptive mesh refinement strategies, and run our simulations on CSCS pitch-dained supercomputer. Glad to see you later if this is of interest for you. Thank you.
Okay, thank you very much. You are even ahead of your time. So next poster is Pierre Blanchard.
Hello, I'm going to present you a poster about randomized numerical linear algebra. And I'm going to describe the potential of randomized SVD on 2 different applications. One is the generation of multivariate Gaussian random variables accelerated by FMM. And the second is the classification of biological species using multidimensional scaling. So if you're interested in linear time SVD,
thank you. You come to your poster, yes, sure. Andreas Jörgsch from CSCS.
Thank you. I'm presenting a poster about hash tables on GPU using log-free linked lists. The application of this hash table will be an adaptive mesh refinement particle in cell method. The log-free linked lists have the advantage that they are fast and that one can make modifications of the hash table without the need of rebuilding it. We outperform the CUDPP library, which is on the web and uses another approach.
Thank you, Andreas. Next is Tobias Grosser.
All right, so I'm going to present PolyACC. This is a compiler technique that allows to automatically translate a sequential software into a hybrid binary that takes advantage of a GPU accelerator if available. So the main focus here is similar to vectorizing compilers. We don't want to regress the full application, but we want to speed up the parts of the application that can actually benefit from an accelerator. So in this work, we integrate different components. This is state-of-the-art polyhedral mapping, a data management library, as well as a general purpose compiler. So
Thank you very much.
Performance, so come and see.
Thank you. Next one is Amore Bunny.
Okay, hi, so I'm Amore Bunny. With my team at Nextflow Software, we're working on fluid mechanics, but using particles-to-particle interaction, which is a kind of generic problem in a lot of fields. With the help of the CSCS, we have been working on accelerator solvers in order to work with GPU. If you want to know the tricks that we have found in order to make it work, come to see the poster.
Thank you very much. You're also ahead of your time. Thank you. Next speaker is Anton Kozhevnikov from CSCS.
Hello, I have a poster about FFT kernel of plane wave codes, where you have to transform wave functions to real space, apply potential, transform back, and so you do it for many bands, many times, and this is expensive. And so I show in the poster that you have to swap wave functions to a two-dimensional grid where column ranks distribute bands and row ranks do FFTs, and then you can scale to 4,000 nodes for a moderate size FFT box, which is, I think, very good.
Thank you very much, Anton. You're also ahead of your time. So Lucas Pospisil.
Hello,
thank you.
Lucas Pospisil. I'm a postdoc from Lugano, and together with my bosses, we are developing new HPC library to deal with large-scale non-stationary modeling problems in econometrics. So if you are interested in our latest progress, so you are welcome.
Thank you very much. Thank you. So thank you for this very prolific poster. Now we have the emerging domains. Okay, so this is gonna be easy. The first speaker is Erin Eftekhari, right?
Yes.
Please.
Hi, my name is Erin Eftekhari. I'm from UZI. This project is made possible with my advisors, Simon Scheidegger and Olaf Schenk. We're concerned with solving high-dimensional economic models. And to do so, we use dimensional decomposition with sparse grid. To solve, using the resources at CS, we were able to solve a 100-dimensional model globally.
Thank you very much. And next one is Maxim Bishkin.
Yes. So exponential random graph models are well-established models for analysis of social networks. And the Markov chain Monte Carlo is required for estimation of parameters of these models. So we developed efficient Markov chain Monte Carlo method for the sampling from the relevant probability distribution. We use parallel tempering for parallelization of the method, and the resulting speed up is up to 3 orders of magnitude.
Thank you very much. So thank you for the emerging domain. And now we have the life science. So please, once again, order yourself in the right way already. So who's number one? Number one is Daniele De Moreno. So wait a second, please, go ahead.
My name is Daniele De Moreno, and I'm a postdoc at UZI. The main goal of my project is to characterize the dimerization process of two chemokine receptors that are involved in several pathologies. We are trying to do this using coarse-grained metadynamics, and all the results of this project are really important in several pathologies. Thank you.
Thank you very much. Okay, next one is Tejas Gandhi.
If genes are what defines life, then proteins are the workhorses through which this definition is realized. Hi, my name is Tejas Gandhi, and I would like to introduce how the current leading technology for measuring proteins and discuss some of the computational challenges surrounding it. Thank you.
Thank you very much. So the next one is Dominic Sidler. Oops. Yeah? 5? I don't know, 2 might not have shown up. Okay, please.
Thank you. My name is Dominic Sidler. I've worked on molecular dynamics, free energy calculations. Usually you can only calculate free energy difference between two states, but we developed replica exchange EDS where we could do that for n states, and I can show you an example for 5 states if you come to my poster. Thank you.
Thank you very much. Next one is Yana Vtec. Thank you.
Hello, I would like to show you how by combining molecular dynamics simulations with Markov state modeling, we can get insights into the process of passive membrane diffusion of cyclic peptide cyclosporin A, which is a drug. So if you would like to see how computational methods explain why the drug works, please come and see.
Thank you very much. Next one is Annick Reneve. Please.
Hello. I use also molecular dynamic simulations of a marine sponge protein to study the effect of chemical modification on the structure. And in one case, we found one modification that was of particular importance, and that can be used to design advanced peptides that can be used as drugs, as antibiotics or anti-cancer drugs. You can hear more.
Thank you very much. Okay, next one is Venmo Lemon. Please.
So I'm going to talk about, if you come to my poster, about how you can make your data available to the general public or the people in your field, so that you can run graph analytic queries on your data, on our data, combine it with themselves without investing in infrastructure or data warehousing.
Thank you very much, ultra fast. There are no other posters. Okay, please go ahead. Present yourself anyway. I'll use the last. Hello.
I sent actually like.
Yeah, well, let's not have this discussion here. You introduce yourself and please.
Hello, everybody. Good afternoon. My poster is a part of a PASC project for high-performance simulation of fluid structure interaction in aortic heart valve. And in this poster, we presented an acceleration of the process on general purpose GPUs on CSCS.
Thank you very much. Oops. Next one, you're not, but please go ahead.
I really do have a poster. My name is Lisbeth, and my poster is, better software, better research, right? I work at the Blue Brain project here at the EPFL, and our goal is to improve our understanding of the brain through simulation. And in that context, we work on software for the synthesis of virtual neuronal morphologies. And if you're interested to hear how we do that, you're very welcome at my actual poster.
Which is number? 4. Number 4. Okay, thank you very much. Now, thank you. Now we have the posters in materials. So please, also there, if you know. Oops. So, we are ready. Mohammed, you go first, please.
Hello, my name is Mohammed Houssein. In this poster, I present the Fourier-based Poisson solver for solving the generalized Poisson equation subject to periodic or homogeneous Neumann conditions at the boundaries of the simulation cell and the Dirichlet type conditions at arbitrary subdomains. And the application is in first principle device simulation, but also for all the boundary conditions, consistent forces are implemented. Therefore, you can perform energy-conserving molecular dynamic simulations. Thank you.
Thank you very much. So the next one is Giuseppe Faccio, please.
So I am Giuseppe Faccio from the Department of Physics, University of Basel. In my poster, I reported our advancement in the developing of an implicit solvation library to extend electronic structure codes to complex environments. So I will give you details of 2 solvers. One for the generalized Poisson equation and another for the Poisson-Boltzmann equation. I will show you results for benchmark calculation about neutral molecules, ions, and structure prediction.
Thank you very much. Next one is Samuel Andermatt, please. Oops.
Hi, my name is Samuel Andermatt. We have enabled real-time DDFT and theorem-based molecular dynamics for large systems. This was achieved through a combination of subsystem DFT and linear scaling techniques that exploit sparsity. The implementation was done in CP2K, and we demonstrate the possibilities on a number of example systems.
Thank you very much. Okay, the next one is Vladimir Ripken, correct?
Sure. I'm Vladimir. I work in ETH at Nanoscale Simulation Group. So humankind has been doing molecular dynamics simulation in classical fashion for half a century, essentially. And recently, due to technical progress in computation and in theory, we learned how to do quantum molecular dynamics. And a lot of surprising things have been discovered, which change our understanding of molecular simulations. Here we present more, which we find surprising, and they have to do with redox potentials in aqueous solutions, which have to do with electrochemistry. So you can learn more.
Thank you very much. You are not in the list, but please.
Somehow my poster, I think, got missed there. But if you come in the section, you cannot miss my poster because that's the most colorful one. So the title of my poster is The Periodic Table of Molecules. And the problem we are working in is when you have large number of structures to work on, how do you visualize all of them together? And so we are building intuitive maps of molecular database.
10
and
seconds.
if you come there, you will see that what it looks like. And and no matter which domain you are from.
The number of your poster is?
2.
Okay, yes. Very good. Thank you very much. Okay, thank you. Posters in physics. Who are the posters in physics? Okay. First one is Darin Reed, who's still coming. Okay, Darin, please go ahead.
Thank you. So radiation and neutrino transport is very difficult in simulations, and that's mainly because the speed of light is very fast, which limits our ability to model black holes, galaxies, stars, and many other problems in astrophysics. So we put together a library that contains many algorithms for this transport, which is often needed when gas varies with a big dynamic range, as in, for example, planet formation. And the PI is Lucha Meyer for this diaphony project.
Thank you very much. This was perfectly on time. Next one is Kirill Pakruski.
Hi, I'm Kirill. So I have a post about how we use high-performance classical computers of CSCS to develop the topological quantum computers of tomorrow, the day after tomorrow. And it's more specifically about fractional quantum Hall effects, so if you're interested, please come see me.
Thank you very much, Kirill. Next one is Christoph Versal.
So my poster is about the fluid plasma turbulence code GBS, which models the edge of tokamaks, which are fusion devices. And in particular, in this poster, I present the way how we go from pure MPI implementation to a hybrid shared memory implementation. At the moment, we have a working version with MPI and OpenMP, and we have first parts of the version that's using OpenACC to go to GPUs. But since we have many different parts of the code, only one of the parts is yet ready for the GPUs, but it shows good scaling.
Next one is Joele Janet.
Hello, my name is Joele Janet. I'm working in Istituto Ricerche Solari Locarno, a research institute in solar physics. In particular, I'm working on the radiative transfer equation for polarized light. This equation is solved by some numerical integrators, which require to be as local as possible in order to favor domain decomposition, and also has to face strong gradient in atmosphere parameters. I will present some of these methods.
Thank you very much. The next one is Shantanu Shah.
Hello, I am Shantanu Shah. I come from University of Basel. So one of the key ingredients in search of new materials is the pseudopotentials. You need some pseudopotentials which needs to be soft, accurate, and transferable. That means it should work whether it's a cluster system or it's a bulk or it's a molecule. So I present here new pseudopotentials which have been benchmarked for the solid cases, for the molecules, and they perform at the level of the all-electron cores. Thank you.
Thank you very much. Thank you. The poster, I think this is the last one in solid earth dynamics. Please. Oops, without killing yourself. Iris, you are the first, please.
Hello, I'm Iris and I'm coupling a geodynamic seismic cycle model and a dynamic rupture model to exploit the advantages of both methods to accurately model earthquakes. We look at both the long-term and the short-term processes. And if you would like to know anything about how we try to model earthquakes, please stop by.
Thank you very much. You are very to the point. Next one is Casper Pranger, correct?
Hi, I'm working at ETH in the geophysics group. And in earth sciences, we frequently use staggered grid finite differences, which are, however, a pain in the ass to program sometimes. And that's why it makes a lot of sense to automate this progress. And I will show you happily how I tackle this problem in my poster.
Thank you very much. Next one is Neslian Othman.
Hello. We aim to image subsurface fluid using seismic data. We use pore-elastic theory, which provides more complete theory, but it also implementation might be very complex. We also use a joint method as an efficient way of computing the gradient of a misfit function. And in the poster, I will show several misfit functions and corresponding sensitivity kernels, which are used as a basis of gradient-based iterative inversion. So if you are interested, please.
Thank you very much. And the last one is Philippe Marty, please.
Hey, I'm presenting a Chebyshev-based fully spectral dynamo simulation, which allows for a significantly larger time step just by treating the actual Coriolis term implicitly, which is basically possible because we have a very sparse formulation of all our differential operators.
Thank you very much. So I would like to thank all the poster presenters, and to make the poster,